Hello, my name is Richard Trainham. I work at Hoft Institute, which stands for House of Tutors. I work as a tutor for math and physics. I am making a series of videos to teach calculus. These videos are oriented towards students taking calculus here at the University of Texas, but they could be used for pretty much any calculus course. Okay, in this first video, I'm going to introduce a little bit of the topics from calculus and get started on one of the first topics of calculus. In calculus, there's two main topics, the derivative and the integral. The derivative is really a way to solve finding tangent lines to curves. And the integral, which will come later in calculus, will be how to find areas under curves. Now, there's plenty of applications for both of those, which is going to be what you study other than just learning how to do the derivative and the integral. But the derivative is going to be used to find the slopes of tangent lines to curves. Now, you're probably already familiar with a slope of a line. You know, if you have a straight line, the slope is defined to be the ratio of the rise over the run, like that. But, and the rise over the run, that ratio is the same regardless of what 2 points on a straight line you choose, okay? Well, that's easy. But what if we don't have a straight line? What if we have a curve? Like maybe a parabola. And I want to know, what is the slope of the line at that point? Now, to be more specific, I mean the slope of the tangent line. The tangent line is going to be a line that sort of touches it at one point, like that, and is heading in the same direction that the curve is heading, really, really close to that point. In other words, if you like zoomed in really close at that point, you know, that would look like the two curves were practically on top of each other, okay? And we want to find the slope of that tangent line. And there's no easy way to do that. I mean, we can't do what we did on a straight line, where we take 2 points on the line and then find the slope, because there's only 1 point you know, on this line where it touches the function. Okay, so to solve that problem, what we're going to do is we're going to first find what's called a secant line to a curve. Now, a secant line is defined to be a line that passes through 2 points on a function, like that, where maybe I'll say that this point is at x equals a, and this point right there is at x equals b. And the curve we're going to call f of x. And so the slope of the secant line would be f of b minus f of a, that's the difference in the y-coordinates, therefore the rise, over b minus a, which is the run. So this is the slope of a secant line between 2 points, x equals a and x equals b. Okay? Well, that's fine for finding a secant line, but we're trying to find a tangent line. Well, the way we're going to be doing that is, let's pretend that this second point, b, I was sort of thinking of b as being a fixed point on the curve. But what if we thought of that as being a variable point, like the x-coordinate is just whatever x is? Okay, well then this equation would become f of x minus f of a over x minus a. Now that we have this definition, and x we're thinking of as a variable, the way we're going to get the tangent line is we're going to make x move closer and closer and closer to a. And what that's going to do is, as x gets closer and closer to a, like the secant line, like between these 2 points, we go like this, and then it gets closer and it goes like that, and eventually it should approach the slope of the tangent line. Okay, now there are going to be wrinkles later, but that's the general idea of getting the slope of the tangent line, which we're going to eventually define as the derivative of a function. Okay, so before we move on to that, let's do some problems finding slopes of secant lines to curves. Okay, so here is a problem. I want to find the slope of the secant line for the function y equals x squared. Let's change that and say f of x equals x squared. And I want to find the slope of the secant line from x equals 2 to x equals 2.1. Okay, so using that definition that we had wrote down earlier, it's going to be f of b minus f of a over b minus a, where b is the 2.1 and a is the 2. And if you reverse those and call the other one a and the other one b, you're going to wind up with the same answer eventually. It's just the top and the bottom would be multiplied by -1, and the negative ones would cancel. Anyway, so if we plug in 2.1 into our function, we get 2.1 squared, which is 4.41. If we plug in 2, 2 squared is 4. And then 2.1 minus 2 is 0.1. If we subtract the 4 from the top, we get 0.41 divided by 0.1. If we just shift the decimal left on both the top and the bottom, we get 4.1. So the slope of the secant line from x equals 2 to 2.1 is 4.1. Okay, let me change this so where instead of from 2 to 2.1, let's go from 2 to 2.01. Okay, it's going to be very similar. I guess I'll just write out, because this is the first time we're doing these problems, I'll write out this structure again. So f of 2.01 minus f of 2 over 2.01 minus 2. Okay, that's going to get put into our function, and 2.1 will get squared, and we'll get 4.0401, and then minus 4 over 0.01, 0.04 01 divided by 0.01 simplifies to be 4.01. Now, notice that when we went from 2 to 2.1, we got 4.1, and when we went from 2 to 2.01, we got 4.01. You may suspect that these numbers are getting closer and closer to 4. And as we make this value get closer and closer to 2, then our slope is going to be approaching 4. And that would be the slope of the tangent line. Although these two are still slopes of secant lines. It's just as you make these 2 points get closer and closer to each other, it'll approach the slope of the tangent line, unless the function is weird. Anyway, so this is finding the slope of the secant line between 2 points. And there is a related problem that is a physics problem, which is finding the average velocity of an object. It could be like an object that you drop, and we're finding out the average velocity between 2 points in time, or it could be someone driving a car, and we have his position as a function of time, and we want to find the average velocity between 2 points in time. Well, average velocity between 2 points in time is pretty much the same as the secant line between 2 points. You know, but like a secant line goes between 2 points, and this average velocity is also between 2 points in time. Okay, so it's actually going to be the exact same structure as the slope of the secant line. Okay, so here is an average velocity problem that we'll be looking at. S of t is -16t squared plus 64t plus 16. And we're going to find the average velocity from 1 to 2. Now, S in this problem, I'm thinking of being the height of an object that we're going to throw up in the air, and it's going to come down over time, initially it's going to be going upwards and eventually downwards. And I picked these 2 points in time pretty randomly. So I don't know, the average velocity might be positive if it's going upwards, or maybe it's negative if between those 2 points in time it's going down. I'm not sure. So let's see. The average velocity, I'll just denote with V average below that, subscript average. That's a little bit too big. Let's make it smaller. There is going to be the difference in the two positions divided by the difference in the two times, where B and A are the two different times, the 1 and the 2. You see it's the exact same structure as slope of a secant line. Okay, so if we plug in 2, we're going to get S of 2 minus S of 1 over 2 minus 1. Okay, S of 2 is what we get when you plug in 2 for time here. If we plug in 2 squared is 4 times 16 is 64, so minus 64. Plug in 2 there, and we get positive 128 plus 16. So all of that is the value of S of 2. Okay, S of 1, if we plug in 1, well, that's a lot simpler. Minus 16 plus 64 plus 16, we can cancel the 16s, leaving 64. But remember, there's a minus there, so minus 64. And then our bottom is going to be 1, which is great. 128 minus 64 is 64 plus 16, but then minus 64 is just going to leave 16. So the average velocity is 16. Okay, so I just use a formula here, but let me explain a little bit more exactly what this formula is doing. Okay, S of 2 is the position of our object when time is 2. And that was all of that, which simplified to be 64 plus 16 is 80. And let's say that S was in feet. Okay, and S of 1 is our position at time is 1, which is 64 feet. And then, so when time was 1, we were at the 64-foot high. And then when times 2, we're 80 foot high. Well, that means that we increased our height by 16 feet. We traveled 16 feet. And we traveled it in 1 second, because from time equals 1 to time equals 2 is a passage of 1 second. That's the 2 minus 1. So the top is your displacement. It's your difference in your location at time A and B is called your displacement, which is not necessarily distance traveled, although in this case it is exactly the same as distance traveled. So it's just distance traveled over time. Distance over time is velocity. Okay, so average velocity problems, as you see, are pretty much the same as a secant line problem, and they're calculated in pretty much the same way. And if they change the problem where instead of from 1 to 2, they wanted you to do it from like 1 to 1.1, we'd just be plugging in 1.1, calculating it. Okay, so I think that's a good place to end this video. In the next video, we'll be talking a little bit more about slopes of secant lines and tangent lines. So hope to see you in the next video. Have a good day.